AUTOSAR. Explained by Annette Kempf.
Hello, welcome to another session on AUTOSAR basic software. Today we will have a look at the communication drivers. So we'll start again with having the orientation. So you will get an introduction into AUTOSAR Classic on a general level, how it's composed, how it's structured. And then we will have a look into the microcontroller abstraction layer, where the communication drivers are a part of. And once we have this orientation and the general view, which we derive from our Embedded Academy e-learning on AUTOSAR, we can then go into the details of the specification and navigate the AUTOSAR page. So for now, enjoy the introduction, and I will be back with you soon.
The Classic Platform is AUTOSAR's solution for embedded systems with hard real-time and safety constraints. The architecture distinguishes on the highest abstraction level between three software layers which run on a microcontroller. The lowest layer is the basic software layer. It is divided into three major layers and complex drivers. The Microcontroller Abstraction Layer is the lowest software layer of the basic software. It contains internal drivers, which are software modules with direct access to peripherals. The main task of this layer is to make higher software layers independent of microcontrollers. The ECU abstraction layer connects the drivers of the microcontroller abstraction layer. It also contains drivers for external devices. It offers an application interface for access to peripherals and devices regardless of their location and their connection to the microcontroller. The main task of this layer is to make higher software layers independent of the ECU hardware layout. The complex drivers layer spans from the hardware to the runtime environment. Its main task is to provide the possibility to integrate special-purpose functionality. The services layer is the highest layer of the basic software, which also applies for its relevance for the application software. It offers, for example, diagnostic services and memory services. Its main task is to provide basic services for applications, runtime environment and basic software modules. Above the basic software lays the runtime environment. This layer provides communication services to the application software. The AUTOSAR software components communicate with other components and services via the runtime environment. The main task of this layer is to make the AUTOSAR software components independent from the mapping to a specific ECU. The application software layer realizes the application functionality. This layer is mostly hardware independent and consists of different software components. The microcontroller abstraction layer is divided into 6 model groups, which group software modules of similar type. In this case, the software modules are internal drivers. A driver is a software module with direct access to peripherals. The internal peripheral devices are shown in the hardware layer. The module group microcontroller drivers consists of drivers for internal peripherals, like the general-purpose timer and the watchdog, as well as functions with direct microcontroller access, like the core test. The module group memory drivers consists of drivers for memory-mapped external memory devices, like the external flash, and on-chip memory devices, like the internal flash and the internal EEPROM. The crypto drivers are drivers for on-chip crypto devices like SHI or HSM. The wireless communication drivers are drivers for wireless network systems, which cover in-vehicle or off-board communication. The module group communication drivers consists of drivers for ECU on-board communication, like SPI, and vehicle communication, like CAN.
Welcome back. So now we will have a look on the AUTOSAR page. So we will dive into looking at the page itself. Currently we still have, while recording, we still have the AUTOSAR Classic release 2311. Maybe when we publish, we might already have the 12, but in AUTOSAR Classic, the changes are not that big anymore. Yeah. Here you can see the microcontroller, which you heard already is not part as itself from AUTOSAR standard. And here in red, you see the microcontroller abstraction layer. And today the topic is the communication drivers, which includes wireless communication drivers and communication drivers like was before. And maybe you know the old picture, the wireless of this splitting up is quite new. And within the wireless communication driver, right now there's only one single specification on wireless Ethernet driver. I would go back nevertheless and then go here into the communication drivers like it was before. And there you find a lot more specifications. So there's a lot on CAN, CAN XL, CAN XL transceiver. You see Ethernet driver, but you see also here within this, it's alphabetical order, the specification on the wireless Ethernet driver. So it's assigned to 2 packages, and I would say is part of the communication drivers as it is. And then like in the other specification parts before, you have also the requirements specifications. We will not train or show you all on CAN drivers and so on, because it's all a complex topic. And usually if you have a deeper CAN training, this alone will take you 1 day on a general level. And the same applies for Ethernet, maybe LIN and SPI, you need less time, but we'll go through and navigate through nevertheless. Here I prepared a little bit, which we will look in afterwards. So we'll have a look at the, where is it now? No, this is double the CAN driver. So here's the CAN driver. As you can see, the specification has 131 pages. And it's not explaining you anything about CAN. So you better learn this before if you need it, and you should really have an understanding on, I would say, serial bus systems. And serial bus systems we also have as a training within our Embedded Academy portfolio, where you get explained all the terms in serial communication, which you need as basic know-how, even if you go through this specification. So I can really highly recommend to take serial bus systems before working on bus systems in general. As the specification is so long, we cannot go into all the details. I will just have a look at the CAN hardware unit. So for the CAN controller, you really have hardware blocks or hardware parts, chips, CAN transceiver, and here you have an example on CAN transceiver A and CAN transceiver B, which then is the CAN bus A. So you can have several CAN connections, and usually you also have several CAN connections, and then there's really the physical channel attached to this. CAN usually you have for the communication in the vehicle, but often you also have CAN for example, for diagnostics, and also for, especially if you're in the combustion engine area or in general also the electrified powertrain, you work a lot with tools, for example, like Inca, to do the calibration of your maps. And this usually is also a CAN connection, which then is only needed during the period of development and not in serious production. So you will have a CAN which you need during the development phase, which then is not needed anymore in the series project itself. But this you also have to consider. So you will have different CAN usually within your system. So this was a look at the hardware itself. So you have a CAN controller and you have a message object mailbox. From a structure point of view, it's the specification like it usually is. You have acronyms, but here acronyms and abbreviations. In this chapter, you also find the priority inversion and the CAN hardware unit, which you might have overlooked in the first place, scrolling down to the real content, because usually the specification takes a lot of requirements, traceability, and all this stuff before you get to the real thing. Then I would like to go to the functional specification of a driver. It's in the naming, it's also the CAN written like this. For me, it's always irritating a little bit with AUTOSAR naming standard. It's the first letter, which is capital letter, and then the small letters. But if you have then the CAN controller hardware, you write the CAN with capital letters again. So on the LPDU transmission, the CAN module writes the LPDU in an appropriate buffer inside the CAN controller hardware. Appropriate buffer, you have to decide according to the size. And there's an own chapter you see below on the LPDU transmission. With all the details and also the message objects of the hardware. And then you have priority inversion again. So this is how to read the specifications, where you have to jump around. But basically you have to look into this in detail yourself, because it doesn't have to skip something. For me, what's really important is this the state machines, and even more important, where do I have a message sequence charts? Now I'm lost myself. Sequence diagrams. So you have a state machines and you have a different states which you need to understand. So the CAN has states, and also your ECU has states. And why is it so important? Because you're not alone in the world. So it's your ECU, but there are several other ECUs as well. If you're talking to someone on other, then the states have to match. Each CAN controller has complex state machines implemented in hardware, like I said before. And for simplification, the number of states is reduced to the following 4 basic states in this description. So you have uninit. What is uninit? It's not doing something, it's not initialized. It's stopped, it's started, and it's sleep. The CAN hardware access is encapsulated by functions of a CAN module, but the CAN module does not memorize the state changes. So you will not have information on when state changes were done. And the CAN module offers the services CAN init to initialize, CAN set baud rate, and CAN set controller mode. For the baud rate, I think this is also important to have an understanding what's bitrate and baud rate. I would again refer to our e-learning on serial bus systems, because all these terms you will learn in a very well presented way, so that you really understand each word what's behind this. And these services, which were just mentioned, perform the necessary register settings. So in the microcontroller, all the registers to be set. So these services perform these register settings that cause the required change of the hardware can control a state. There are two possibilities for triggering state changes by external events. It's either a hardware bus event, a bus off event, or a hardware wake up event. And these events are indicated either by an interrupt or by a status bit, which is then polled. So you can decide on polling or on interrupt. In the can main function bus off or can main function wake up. I would stop here for now, and I would like to have a look also in the topic of sequence diagrams. So in general, this is not only connected to CAN, it's in general a topic you should have always an understanding on your states, understanding the state of your ECU, the state of the communication, and what it means to the states to the other ECUs. The advantage is that these states, and we'll have also a look at the sequence diagrams, are defined in the same way for all the ECUs in a vehicle, because if you would have different standards, then it would be really difficult. But this way the states are defined and you have a clear understanding. If it's like a TCU or a battery management system or whatever, you always have like the same understanding on your states. So for sequence diagrams, we go on sequence diagrams and we find almost nothing. It says interaction between CAN and CAN interface module. For sequence diagrams, see CAN interface module specification. Okay, we'll have to go to the next specification. And concerning the wake up sequence, it's referring to the ECU state manager. So where's the ECU state manager? The ECU state manager is not part of a microcontroller abstraction layer, but you will find it in the system services. So ECU state manager is in the system services, and we're now going to, now I have double. Now I'm lost. Then we'll just start again, clicking it, So we have a system services, and within the system services here we find the specification of the ECU state manager. So it's a very small specification. It just has 217 pages. And where to find, We have the sequence charts here. And there are some figures, like the startup phase, start pre-operating system sequence, and so on. And what we are now starting is with wake up. Everybody who worked longer with in the automotive domain knows a lot about going to sleep and wake up, which often, if for people who worked in industry, is not so easy to understand. But the thing is, if your vehicle is parked for example, you're on vacation and it's parked for 4 weeks, and then you don't want all the ECUs in the vehicle to be awake, because otherwise when you're coming back, you will not have any battery power left. So this sequence, it's not so easy, because the whole ECUs within a vehicle have to wake up step by step, and also go to sleep step by step. So you don't want to have malfunctions. You want to have the ECUs available, which you need right now. Yeah. So this sequence is not like easy peasy. It's really something which is coordinated, and the wake up sequence is on all the ECUs, and of course within your ECU where you are in the right order. So thinking about this topic, when I started automotive, I came from a different field where the machines are active all the time. So then it's not so easy to understand why this topic needs so much understanding and taking time to really understand the flow and the sequence. And from this point of view, I think it also makes sense that it's not part of the specification of the CAN driver, but like in a central specification. So here you have the wake up sequences step by step. I can click here, and then you see that you have these state sequences, and you have a wake up sequences, and you find quite a lot here. So first on the general purpose timer wake up, yeah, for the ICU wake up, and then you have the different communication drivers: CAN, LIN, FlexRay, and Ethernet, where you have the state diagrams, yeah, sequence charts, yeah, and this is how it looks like, the sequence charts. I think this is you need to zoom in in your specification to understand it, but I would highly recommend to understand this. So approaching CAN and reading the specification in AUTOSAR, it's a lot of details, how to configure and so on. But to approach this topic, first learn the terms on serial bus systems, all the things you need to know. What is a parity bit? What is CRC checksum? What is different kind of clock configurations? Was it bit rate, baud rate, and so on? So that you have a basics there. Then the next step would be to understand exactly the protocol where you're working on, like CAN, LIN, FlexRay, Ethernet. Most is not that much used anymore, so to have an understanding there. And when you approach these communication drivers, to understand which states I'm in, with whom do I communicate, when do I have to be active, and also with the wake up and shut down or going to sleep sequence, that you have an understanding that it's the right order. Yeah. So this for now, considering further specifications in this area, I would like to have also a sneak peek into the SPI, because I would say SPI is a little bit different. Why? Like with CAN, FlexRay, LIN, Ethernet, you usually communicate to other ECUs. Yeah, so you communicate to the outside, and with SPI, and there's also for example, in modern Infineon microcontrollers, there's MSC bus and others, direct buses. They usually communicate within your ECU. So you exit the microcontroller, but usually you don't exit the electronics. Yeah. To have a look at the SPI handler and driver, and it's still quite a big specification which you are seeing there. Yeah. I don't know why I don't have a navigation line there. Yeah. And then you will have a short look at the functional specification. And there you have an overview on the functionalities and features. And for SPI, you usually, where you often have SPI in the practical part is, I, for example, worked in the combustion engine powertrain domain before, and we had so many sensors and actors that the microcontroller pins connecting directly to low side or high side drivers were not sufficient. So there were not enough pins. And then we had a lot of low side driver ASICs, for example, for the digital input and digital output. And then you communicate the status, how to change the pin via SPI. So this is one approach. Or for example, the safety microcontroller, which is monitoring functional safety according to ISO 26262. This usually is also an ASIC. For example, IEC 61508, which Infineon was providing, and 61508 is the general standard where the ISO 26262 was derived from. So now again, to have a look at the SPI driver. So you have a simple SPI, you also have a queued SPI, and you have also a DMA. With SPI, you can also have chips which you are putting in daisy chain. So it's like you have 3 or 4, for example, in a chain, and you only have one SPI connection for several of these controllers. So you go from your microcontroller to connect to several of these drivers or chips outside via SPI. So it's these use cases which are identified, yeah. And this SPI handler driver allows getting a simple software module that fits simple needs to a smart software model, and it can be also enhanced. Yeah, so it's then these different levels are defined. Yeah, to have a scalable functionality for the SPI handler driver. So you have a simple synchronous SPI handler driver. So then the communication is based on synchronous handling, and it's using a polling mechanism with a FIFO, first in, first out policy to handle multiple accesses. So buffer usage can be configured to optimize and to take advantage of whatever hardware capabilities you have. The level 1 is basic synchronous SPI handler driver. And then the communication is based on, I said synchronous, it's basic asynchronous SPI handler driver. So the communication is based on asynchronous behavior using either interrupts or also a polling mechanism, which these things are selectable even at execution time. So you decide before, and with a priority policy to handle multiple accesses. Yeah, and the buffer usage configuration is the same as before. And the level 2, so even more enhanced, it's enhanced synchronous asynchronous SPI handler driver, and the communication is based on either synchronous or asynchronous behavior using either interrupts or polling mechanism, and a priority policy to handle multiple accesses. Yeah, and the buffer usage is the same configurable as in the upper levels. Yeah? I would say more or less, here is a nice picture of how SPI communication is working, which you're not having in other specifications. I think it's a very nice thing to see. So you have the clock, yeah, and your MOSI and MISO line, yeah. For the clock, it's also you can decide on which I'm just lacking the English word when the level changes, at which flank, yeah, at which flank you want to do what. So you still have quite a lot of configuration possibilities. And for this, I would also highly recommend to take some SPI training before. Yeah, then I would say I go back to the overview. It's a lot of specifications, and of course, within the short time, we can go through everything. So more or less get an understanding on serial bus systems, on your system you want to configure. Focus on the state machines, on the message sequence charts, have an understanding on what wake up and going to sleep means. And then I think all the rest of the configuration, it's just finding the API interface which you need and to configure it accordingly. And for this, these specifications are a very good indication, but you need to have the overall picture before. So I hope this short look into the different parts of communication drivers is helpful for you. And the next session then will be on I/O drivers. Thank you for joining today. So next time we'll go to I/O drivers, and I hope you will join again. Thank you and bye-bye.
If you want to learn more about AUTOSAR and other interesting topics, go to embedded-academy.com.